Good morning, everyone.
Good morning.
How you doing? Any questions, concerns, comments, etc. before we get started today? All right. So, last time we began going over Newton's three laws of motion and how they relate to force, mass, and acceleration. To briefly look over them again. Newton's first law states that an object at rest remains at rest, or an object in constant motion stays in constant motion unless acted upon by an outside force. This is because matter is lazy, and whatever it's already doing, it wants to keep doing. You literally have to force it to change. Second law is a formula, a very useful formula, and force equals mass times acceleration. And lastly, third law, for every action force, there is an equal and opposite reaction force. For this course, you do need to know the laws. You do not necessarily need to memorize them verbatim, but you should remember the gist of each law by number. How this will matter on, say, tests and homework is, out of all three of the laws, you should know this one the quickest. It's a formula that we're going to use pretty commonly. It's written on your formula sheet. You can even write second law on your formula sheet. So that's going to come up all the time. Additionally, again, test one is in about a month now, just shy of a month. And on test one, there will be a question where you do have to identify each of these laws. Again, you don't have to memorize them, strictly speaking. You don't have to be able to write them from memory. The way that I do it on the tests to save time and energy is I write out 5 statements, and you have to pick which 3 of them are laws of motion and correctly number them. 2 of them will be distraction statements. Maybe they're true, maybe they're not. 3 of them are laws of motion, possibly written in slightly different verbiage, and you have to be able to identify them. So again, I'm looking for meaning and interpretation rather than memorization. Yes?
Can we write them on our formula sheet?
No. That's one of the few rules. Yes?
Can we write like with the triangles and stuff, if we don't really know the formulas that well, can we write it on a formula sheet?
Like Sophotella?
Yeah.
Yes.
But that's all we can write, just Sophotella.
You can write lots of things. One of the few things I'm saying don't write is just these paragraphs. Because that is one of the few things I do want you to be able to, again, not recite from memory, but at least identify from memory. Does that sound fair?
Yes.
Okay. It's one of the few things that I don't just tell you to write on your formula sheet. Any other questions at this point? All right, so the laws are all very important. We're gonna use them from now till the end of the course. And to start off today, let's get in a little bit more practice utilizing them before we start looking at individual types of force. Here we have a box being pulled in 4 different directions at once. Again, this is basically a free body diagram, just a fancy way of saying it's a drawing with arrows that represent all of the forces acting on something. I'm envisioning this kind of like a bird's eye view of a 4-direction tug-of-war match. 500 gram box being pulled in 4 different directions. And I would like you guys to tell me, 1, what is the total force acting on this object, and then 2, what is the total acceleration of the object as a result. I'll give you guys a couple of minutes to ponder this on your own before we discuss or move on? Yes. Mhm.
Sorry, just hold on. So, you would want to divide by mass on both sides. That would send it into the denominator on the left. And that would be the next step of algebra. Just a few small issues that I'm going to address now.
Okay. So this box is being pulled in 4 different directions simultaneously. As things tend to work in tug of war, all these forces are pulling in opposite directions, or we have 2 pairs of opposite directions working against one another. So before addressing even the numbers, looking at all the forces here, what direction do you expect this box to start drifting in? The right, correct, but also down. So down into the right. More down or more right? More right. So east, southeast, approximately. Does that sound fair? So, with that expectation, we should be shooting, we're going to be on the lookout for an answer that matches that general direction. So, we want to find the component form of the total force acting on this object. We've got 4 forces here, all of which point in different directions and different axes, and so this is basically the same vector addition we've already done, because forces are vectors. So like when we were adding up displacement and velocity vectors, we need to add up these vectors, making sure to keep each one within its own axis with the correct sign on it. So I'm just going to list these going in sort of the standard mathematician way, starting at positive x and rotating counterclockwise around. That 250 Newton eastward pointing force has no y component, so I'm going to list it as 250, 0. Next, rotating around, we've got 100 newtons pointing up or north. It has no x component. Now there's that 200 newtons pointing opposite the 250. They're in the same axis, but they oppose each other. So whatever sign you put on the 250, the 200 needs the opposite sign. And then the 125 similarly has no x component and points opposite the 100, so it needs the opposite sign as the 100. So these are just the 4 individual vectors listed in full xy component form. If something exists entirely in the x, it does not have a y, and vice versa. And as we did with displacement vectors, we can just literally add them together, making sure only the x adds with x and y with y. So, rather than all these forces literally just becoming one giant number, different parts are working against one another, and so the final result is going to be smaller because they're all working against each other. You get one big answer if they were all working together pulling in the same direction, but here what we're going to get is 250 plus 0 minus 200 plus 0 is going to give us positive 50 in the x, and in the y, 0 plus 100 plus 0 minus 125 is going to be negative 25 in the y. So this is a force vector, and we're going to measure force in newtons. So this is the component form of our force vector answer. Since force is a vector, we can look at its components like we do with displacement. And to kind of represent that number graphically, starting here like an origin point, 50 newtons in the x, 25 newtons negative y, so down. And so the final force vector would look like that, like we anticipated, pointing left and down, more so left than down. How do you feel so far? All right, so this is the component form of our final force vector. We could do magnitude and direction. We could find the hypotenuse of the triangle, but right now I'm just asking for the component. Now that we've found the component form of our net force, what then would the total acceleration of the object be? Since the net force points in that mostly left, a little bit down direction, the resulting acceleration is going to point in that same direction. Because according to Newton's second law, net force equals mass times acceleration. Force and acceleration are both vectors. They're the only two vectors on either side, so they share a direction. So, we know the net force, we know the mass of the box, we want the acceleration of the box. Since we've got the two components, we're just going to use the formula twice, once for each axis. So net force X is that 50, and that's going to be equal to the mass of the box times the acceleration. A is what we want. So we're good to go, right?
No.
No. What's the catch? Kilograms. Very good. I listed that box as 500 grams. How many kilograms is that?
0.5.
Thank you. I'm going to write that as 0.5 just so it's easier to see. So 50 equals 0.5 times A, specifically A in the x-axis. So I'll just label it. Therefore, 50 over 0.5 equals our x acceleration, and that is 100 meters per second squared to the x. Feel good so far? All right, now that's just the x-axis, because it is also being pushed in the y, so it will also accelerate in the y. Since we didn't find a hypotenuse and kept the axes separate, we just have to calculate the two accelerations separately as well. But formula will look very similarly, just use the y force instead. And the y-axis acceleration is negative 50 meters per second squared. So, the component form of our final total acceleration vector, 100, comma, negative 50 meters per second squared. Gesundheit, whoever sneezed. Questions, concerns, vague feelings? Yes.
So like if this is on a test and asks us for acceleration, like you want two numbers, it would be two values always.
Not always. There is in general two ways to write vectors. One is as a component, as in its two components. The other is as a magnitude and a direction. Here I specifically listed find the component form, and that specifies which one I'm looking for. Sometimes I may say what is the magnitude and direction of the final vector, and that will again tell you, if you get to this point, you then have to find hypotenuse and angle. If I'm not specific, either way is a correct way to describe a vector, but you should pay attention to if I do ask for something specific. Does that answer the question? Okay.
When setting that up right there, how do you figure out which force of Newton goes where on the X or Y?
I tend to use the orientation that most mathematicians use. So, does this look familiar? So, most mathematicians define straight right as positive x and straight up as positive y. That's just enforced into my head. Technically, you do not have to do the same thing. You could draw a different axis and label it differently, as long as you pick something and are consistent with it. If you just decided one day, I'm gonna call this z, and this is omega, and this is negative for some reason, that's okay as long as you are internally consistent about that.
So it doesn't matter where you place these though?
Strictly speaking, no. The main important thing is, in this specific case, these two are in the same axis but opposite directions, and these two are in the same axis and opposite directions. Because the numbers would work out the same if you switched x or y, or switched which one was positive and which one was negative, as long as you were consistent about these two are in the same axis and pointing away from each other, and these two are in the same axis and pointing away from each other. That's the main thing I want you to be able to look at the image and determine. Does that answer the question? Now, that said, I use this a lot. This is gonna be my default when I'm doing things on the board. Write this in the upper corner of your formula sheet if you want to, if you're not used to thinking this way. You don't have to use it exactly that way every time, but it's the way I default to, so you're gonna see it a lot. Any other questions? All right. Newton's law is feeling okay as a whole so far. Collective nodding, good to see. Now, Newton's laws apply to all types of force. And an interesting thing about force is that there's lots of different types of them. They all behave similarly. They all do the same things. Regardless of what type of force you're looking at, where it comes from, what type of object it's acting on, they all do these key things. They all interact and add up the same way to create the same final outcomes. But within physics, we have identified different types of force and different sources for force. And they all do have their own unique little quirks, understanding where they come from, how they are commonly used in the world around us. So the main thing we're going to be doing moving forward within this chapter is looking at specific types of force, where they come from, how they interact with the broader whole of Newton's laws of motion. And we've already discussed a few of the specific types of force. Easily the most common specific source of force that we have looked at so far is gravity. So, gravity is a force. I want to make that clear. There is a force of gravity pulling on every object, organism, thing on Earth that has mass. And that force is going to depend on the mass of that object. Now, whenever I'm looking at a specific type of force, I usually label it as F with a subscript. So F because it's always force, and most forces can be used in the same places in formulas. So it's still a capital F, but I use a subscript to be more specific as to what type of force it is. So when I'm talking about gravity, I usually call it F with G as a subscript. So Fg, force of gravity. And force of gravity is once again a synonym for weight. The weight of an object is the force that gravity pulls down on it with. And how you calculate that force on planet Earth is you take that object's mass in kilograms and you multiply it by negative 9.8 meters per second squared. That lowercase g stands for negative 9.8 meters per second squared. But I will write that down in case you have not written it down yet. The definition of lowercase g in physics math is it is a dedicated variable set aside for the acceleration of gravity on Earth's surface. If there's any constant in this class that you end up memorizing accidentally, it's going to be that. That value is, once again, the acceleration at which objects fall on Earth's surface, specifically only its surface. I'll talk more about that in a second. And one of the ways we use that number in physics is if you want to know what something weighs on Earth's surface, you take that number, you multiply it by its mass, and that tells you the force of gravity that creates that acceleration. So anytime any question asks you how much does something weigh, what is the force of gravity on it, that is how you find it. This is again a further differentiation between weight and mass. You use mass to calculate weight. They are not the same thing. Mass is the amount of matter contained inside of something, which is not a vector. Force of gravity is the force that gravity is currently using to pull on that object, and that is a vector, because all forces point somewhere. Gravity points towards Earth's core. Questions so far? Okay. Now, if a question happens on planet Earth, you can automatically assume this is the acceleration of gravity, and you can use this to find its weight. That's a free assumption as long as something happens on Earth. The only disclaimer for that is this number stops being true if you leave Earth's surface. That includes going up, but it also includes going down. The closer you get to Earth's core, the stronger gravity gets, because you are closer to the mass creating the gravity. It's why there's magma under the Earth, because not only is the gravity is so intense that everything is under such pressure that it superheats and melts. So, gravity is a force. Force of gravity acting on an object is mass times 9.8. Every object with a different mass has a different weight, and we use negative 9.8 to find what that weight is. That weight is basically the force needed to cause the acceleration of negative 9.8 in the object in question as it falls. Feel okay with what gravity is for right now? Okay. I'm just very particular about making sure that my words are organized when I'm describing that. There's a lot of misconceptions about gravity that I try to avoid. The next very common form of force that we will be using in this class is normal force, and we're talking about it as kind of a pair with gravity because they do kind of act as a pair sometimes. I believe I mentioned normal force on Monday, but I want to make sure you've seen and written down the formal definition for it. Normal force is the force a surface exerts perpendicularly out of itself to counteract a force exerted perpendicularly into itself. On Monday, I referenced an object that is sitting still on a surface, and that can include humans sitting in chairs or just standing on the ground. Whenever you do that, whenever you are literally on a surface and it is supporting you, you exert a force down into that surface just by virtue of gravity is pulling you down. You don't do it consciously, it just happens. And if you'll recall, Newton's third law states whenever one thing pushes on a second thing, the second thing pushes back. So because of Newton's third law, whenever you physically stand or sit on something and push into it, it will push back up. And that upward pointing force is what is pushing up on you and allowing you to not fall through the object by counteracting gravity. So, free body diagram of you sitting in your chair. Your weight pulls down, normal force from the surface points up. Ideally, they add up to zero and you don't go anywhere. This is true any time you are ever sitting or standing still. Frankly, this is true even if you're walking forwards, as long as you are not actively ascending or sinking into the ground or breaking the chair that you're sitting in. This is happening. Yes?
How does it like always equal zero if we're all like different weights? You know what I mean?
So, your own weight depends on your mass, just per this formula. And whatever that number is going to be the force that you are exerting into the surface. And the surface doesn't really care what the force is. If you're pushing into something, it's gonna push back with the same amount. Just by, again, definition of Newton's third law. We'll tap back to that, ignore that. There we go. Newton's third law. For every action force, there is an equal and opposite reaction force. The way that I think about Newton's third law is, if A acts on B, then B must act equal and opposite on A. So if your body is physically pushing into a surface, that surface pushes back up specifically on you. And since that force is acting on you, we add it to the free body diagram of forces acting on your body, and it usually acts as a perfect counter to the force of gravity pulling down. The only times where these two things aren't equal and opposite are, again, if you're standing or sitting on something that cannot hold your weight, in which case it breaks and you just fall through it. Also, they are not equal and opposite on inclines for reasons we will discuss in the coming weeks. And this weirdness is why you slide down ramps. But we'll talk about that later after normal force feels more normal, pun intended. Did I answer the question? Okay. So whenever I say normal force, I'm referring to the force a surface exerts up as a counter to it being pressed into. And this happens again anytime a surface is pressed into for any reason. You standing or sitting on it, you exerting an active amount of force on it, like pushing down into the counter or the table on purpose, even just leaning against a wall, even, again, I did Taekwondo, do a lot of punching and kicking examples. Punching and kicking, there's a normal force back on you whenever you, again, interact with the surface. Back quick. Did I mention why we call it normal force on Monday? Where the name comes from? Okay. Now, if it helps, you can think of normal force as something normal, as something that just happens automatically around you all the time. It's common, it's just a thing that exists all the time. It is a normal thing. If that definition helps you, by all means think of it that way. However, the source of the word actually comes from mathematicians being very persnickety. I say this as a persnickety mathematician. In math, the word normal does not mean typical. The word normal means perpendicular. I don't know why. Mathematicians have like 4 different ways of saying perpendicular. You've got perpendicular, normal, orthogonal. I don't know why there's so many ways to say the same thing. Point is though, in math, normal means perpendicular, and the reason we call it normal force is because it's always perpendicular to the orientation of the surface creating it. So if the surface is oriented horizontally, left to right, the normal force it creates is going to point in the y-axis. Again, right angle, perpendicular to the surface creating it. So that's the official reason why we call it that. Is that okay? All right. So, let us get in some sample work for that information, because I gave you at least one new formula. We have a 100 kilogram block sitting motionless on a table. First question, what is the net force acting on that block as it sits there? Good guess, hold on to that. 0, very good. Why do we think the net force acting on this object is 0? Motionless, very good. Current velocity is 0. It's remaining at 0, which means the acceleration is 0, which means according to Newton's second law, net force is 0. Motionless definitely means not accelerating. Not accelerating means net force of 0. This means this box is currently in equilibrium. Everything that is currently acting on it adds up to 0. Questions for that first one? All right. Now, based on that information, what is the magnitude and direction of the force of gravity currently acting on this object? It's got to point down, so I'm going to add that to our free body diagram here. And how do we calculate the force of gravity? Very good. M times G, G being negative 9.8. So Fg, I gave you kilograms this time, you're welcome. 100 times negative 9.8. So the weight of this object is negative 9,800, right? No, 9,800. 98, dang it, 980.
980.
I'm having a brain fart
980.
moment.
980.
Thank you. This is a sign I'm dehydrated. The negative means down. I want to make that clear. I always keep the negative there because it's always true, because gravity always points down. Even if you go to another planet, even if you rotate your perspective, it still points to the center of the Earth. Stay hydrated, everyone, especially if you talk for a living. Questions finding the weight of this object. Sorry? Okay. That is its weight. Clear that as a 9. If I ever ask you for the weight or the force of gravity, and you give me this, I will be very sad. Again, this is the acceleration of gravity. We use it to find the force of gravity. Sound fair? All right. So, that is the block's current weight pointing down. That force definitively exists. We can't really escape gravity living on this particular planet. Now, meanwhile, we know the net force acting on this object has to be 0 because it's not accelerating, and yet here's this non-zero force acting on it. So my next question, what is the magnitude and direction of the normal force from the table currently acting on this object? Very good. I am going to show math for getting to that conclusion. I'm going to write out the definition of net force real quick. The mathematical definition, a formula for it. The net force acting on anything is by definition the sum of all the forces currently acting on the object. We only have y-axis forces here, but I'm going to be specific and label it anyway. So the net force in the y-axis on this object, to find that, to write it out, you literally just take all the individual y-axis forces present and literally just add them together, one after the other, addition style. So Fg plus Fn. That is, by definition, the net force. Either they're moving tables or they're dissecting a whale. Place your bets. Didn't know we had the budget for that. Explains why they aren't paying me. They had to buy the whale. So, again, this is as close to a formula for net force as there is. Net force is just all the forces added together. Less of a formula and more of a concept or a rule. So here, we know what the net force is equal to, but we also know what comprises it. So these two things have to add together to create the net force, which happens to be 0. So I'm kind of building a formula. These two things add up to the net force, and we know from prior knowledge that number, that numerical net force, is 0. Therefore, if we want normal force, we know gravity, and we know what happens when you add these two things together. So, if we plug in the weight that we already found, we can solve for that net force. The answer is pretty straightforward here, but it'll get more complicated when we start adding more forces on in future examples. So, remember that you can do this. You can treat normal force as addition equals number. The normal force here is going to be positive 980 newtons. Same magnitude, but opposite direction, and that is why this box does not shatter the table that is sitting on. How's that feel?
I don't understand the FN and FG, like what, I know FG is weight, but what's the difference between them?
So this is weight, this is
Oh.
force of gravity down.
Normal. Okay.
Yeah, sorry, this is normal
Oh,
force.
yeah.
FN, force normal.
Mhm.
I will also point out, this is a bit of an inconsistency. Sometimes, like resources you look at online, or possibly even the course formula sheet, may just call it N instead of FN. Yep, no, formula sheet has N. So, FN or just capital N means normal force. Add that in my notes real quick. So, had it right there. FN or just uppercase N, both refer to normal force. Since the formula sheet says uppercase N, I'm going to try to be more consistent about using just N. Questions, concerns, etc.? All right. There's one last detail I'd like to point out for today before we call it. Gravity and normal force often act as counters to one another. They do tend to be equal and opposite, but they are not by definition equal and opposite. There are several cases where gravity and normal force may neither be equal nor opposite. Now, again, if you're sitting still on a surface or even moving side to side on a surface, they will be most of the time, but again, they are not defined as opposite. There are times where they are not equal or opposite. I want to point out those times to help you build your frame of reference. Let's look back at this particular object as it's sitting on a surface, and let's say that we are going to set an additional box on top of it. So just plop an extra 50 kilogram box on top. Is that going to change the weight of this object? Does it change how much gravity pulls on just this 100 kilograms?
Changes the force.
It changes the overall force acting on the object. You're absolutely right. That box is under more force than it was, but the individualized force of gravity on the first box doesn't technically change, because force of gravity depends on that box's mass and its gravitational pull of the planet. Neither of those changes when you put something on top of it. Yes, there is more total force, but the specific weight of the box didn't change, because it's still the same mass on the same planet. Now, counter question, does the normal force acting on the box change?
Yes.
Yes, its weight doesn't, but if you put an extra box on top of it, that's going to push down harder into the first box is going to push down harder into the table. And likewise, the table is going to push harder back up. So in this revised free body diagram, I'm going to make a separate picture. You've got The box is weighed down. You also have the 50-kilogram box pushing down on this object. That's two separate, distinct downward pointing forces. They don't combine into one superweight. They are still distinct. They do add up to a greater force, but they're still distinct. And in order for the box to not crash through the table has to exert an even bigger normal force to hold the box in place. So the normal force increased even though the box's weight technically didn't. Sound okay? Okay. Now, the inverse can also happen. You can partially lift an object in order to relieve the tension that the table is under, to reduce the amount of normal force required to keep it in place, but that also still does not change its weight. Let's say I come along, this box is sitting here on the table, and I just try to lift it. I'm not successful. If I exert 400 newtons, that is not enough to lift the box this heavy. So I'm sitting here struggling. It's not actually going to lift anywhere. But I am still adding on an upward pointing force. As a result, normal force doesn't have to work as hard to keep the box on the table because I'm helping it. I'm taking some of the pressure off from normal force. There still needs to be a lump sum of vertical force to cancel out gravity, but the table doesn't care about gravity. The table just cares how hard is it being pressed into. So if I exert a 400 Newton upward force, I kind of reduce the weight the table ends up receiving. The weight is the same, but the table doesn't receive the full brunt of it anymore. If this sounds a little weird, I'm going to compare it to something that you may have done in the past. Say there is a bathroom scale right here on the floor, and I step on it. And under normal circumstances, it should read a force equal to my weight. However, does that reading stay accurate if I grab the edge of this counter and lift my feet slightly off of the scale? No. Now, does that actually change my weight? Does that change the amount of matter in my body and the gravitational pull of the earth? No. All it does is it lifts me partially off of the scale, and as a result, the scale doesn't have to exert as much force to hold me up. Secretly, all scales do is tell you the force that the scale has to exert when you step on it. That's why the number changes if you use the counter to lift up, or even use the counter to push harder down. Pushing down, like using the counter as leverage to physically push harder into the scale. I'm not the only kid that did that, right? Like, use the counter and just see the number go up and down. Whether you're pushing up or down, you're changing the amount of force that goes into the scale without actually changing your weight. And because that changes the amount of force the scale has to absorb, that changes the normal force it has to exert back. And secretly, all a scale reads is the normal force it creates because it doesn't care about gravity, it just cares how hard you're pressing into it. Again, using the counter like that to change the number doesn't change your weight, it just changes the normal force. So this is proof, I intend it as proof, that normal force and gravity are not by definition equal and opposite. They are most of the time, but not all of the time. And you need to be aware of that because there will be cases coming up soon where they are not equal nor opposite. Normal force is kind of weird, so we'll continue to describe and define it moving forward. Questions for right now? All right, let me know if you guys need anything. Have a wonderful day. It starts at 6 and I live an hour away, so I have to head home by then.
Yeah. Do you have like, a reference
Well, I record all my lectures, so all of the lectures are online. Granted, that might just be the same information you've already heard. I do give the same lecture 3 times a day, so maybe one of the alternate recordings might be at least slightly differently worded. Otherwise, though, you're always welcome to email me, find me at my office. I can even just Google, conference call you, if you want me to describe something for you.
I just need to tell someone like depth of problem.
Yeah.
So then I did like
Never
15,
hesitate to
12,
contact me.
10.
Even if I don't get back to you quickly, I want to at least figure out when we can meet.
Yes, sir. Thank you.
You're welcome. Yes, absolutely. That is, yeah. These are both correct ways of describing the vector. I was just demonstrating this. But yeah, I like that. That is good. Awesome.